How does 1 single gallon of water shatter a 30,000-pound engine block? This is the forensic autopsy of the 10 hydrolocks that represent the worst failures in heavy rail history. To pull 15,000 tons of freight, a modern diesel locomotive relies on a massive forged steel prime mover. Inside that engine block, heavy pistons compress air and fuel to create thousands of explosive horsepower. It is a masterpiece of American heavy iron. But that indestructible steel has one fatal, invisible weakness: water. If a simple coolant leak drips into just one cylinder, the physics completely change. Water cannot be compressed. When that massive piston slams upward into an incompressible wall of liquid, the engine does not just stall. The 500-pound steel connecting rod violently snaps in half. The spinning crankshaft shoves that jagged steel right through the cast-iron engine block. How does soft, harmless water physically saw a multi-million-dollar machine in half? And what happens when a 4,000-horsepower leviathan violently tears its own guts out? Water inside a diesel cylinder is not a nuisance. It is a barricade. The technical term is hydrostatic lock. When a piston moves up on its compression stroke, the expectation is air, compressible, yielding, designed to absorb force. But water is a different matter. The bulk modulus of liquid water is 2.2 gigapascals. That means it takes over 2 billion pascals to shrink water by just 10%. In a locomotive prime mover with an 11-liter cylinder, even half a liter of water, less than a full bottle, creates an obstruction that will not move. The piston hits, and the pressure spike is immediate. The calculation is simple. The change in pressure equals the bulk modulus times the fraction of the cylinder's volume occupied by the liquid. With half a liter trapped in a cylinder, the pressure rise approaches 1,000 atmospheres. That is over 14,000 pounds per square inch. The steel of the connecting rod, the cast iron of the block, the head gasket, none of it is rated for this. The piston cannot compress the water. The crankshaft, still spinning, tries to force the rod through the incompressible wall. The result is not a stall. It is mechanical violence. Hydrostatic lock is not an engine drowning. It is an instant physical collision. The rod bends or snaps, the crankcase cracks open. The block fails at the weakest point, driven by a pressure spike that exceeds any normal combustion event by orders of magnitude. The laws of physics are not negotiable. Water in a cylinder is a solid wall. The only question is how much force the rotating assembly can deliver before something gives. Even a small volume of fluid, half a liter, is enough to shatter a 30,000-pound engine block. The rest is just metallurgy and math. A 16-cylinder locomotive prime mover is built to absorb punishment, but the real threat comes from the energy stored in rotation, not from combustion. At starter motor speed, the crankshaft turns at 200 revolutions per minute. The moment of inertia for a block this size is about 9.8 kilogram-meters squared. That gives a kinetic energy of roughly 2.1 kilojoules, barely enough to light a household toaster for a second. If a hydrostatic lock occurs here, the connecting rod will bend or snap, but the rest of the block might survive. The damage is brutal, but isolated. Now push the throttle to notch 8. The engine spins at 900 revolutions per minute. The same crankshaft, same rods, but the kinetic energy soars to 43 kilojoules. That is a 20.25 times increase. The numbers are not abstract. At full throttle, the rotating mass stores enough energy to drive a steel rod through cast iron, to rip open a crankcase, and to scatter fragments across the engine room. This is not a gradual build. Rotational energy scales with the square of the speed. 5 times the revolutions per minute means over 20 times the stored energy. When a piston strikes an incompressible wall of water at 900 revolutions per minute, there is no buffer. The force travels through the rod, into the crank, and out through the weakest point in the block. The rod yield strength, around 1,200 megapascals for high-strength steel, is a design limit, not a guarantee. A hydrostatic lock at notch 8 exceeds that threshold instantly. The original equipment manufacturer line is blunt. The 710 series is rated for a maximum cylinder pressure of 40 megapascals. Hydrostatic lock can drive that to 1,000 megapascals. No engineering margin covers that gap. The difference between a cold start lock and a Notch 8 lock is not just severity. It is the difference between a localized break and total structural annihilation. This is why every incident review starts with one question: what was the engine speed when the piston hit the wall? Rainwater and coolant do not care about scheduling or maintenance logs. In Halifax, a drainage pipe ruptured overnight. By dawn, a gallon of water had pooled in the intake gallery of a GP9 prime mover. The shop foreman arrived to find starter motor amperage spiking. The cylinder number 3 hit the incompressible wall. The piston stalled instantly. The connecting rod bent, then snapped. The crankcase cracked open. $2 million in damage, all from a single missed drainage inspection. The incident log reads: hydrostatic lock on cold start, rod fracture, block breach. No injuries, but the locomotive was out of service for months. The foreman said, "You cannot compress water. It is like running the piston into a steel plate." Albany was worse for the passengers. Rainwater from a failed collection system seeped into the intake of an ACS-64 hybrid overnight. When the engineer keyed the starter, the system recorded a current surge. The cylinder number 4 locked. The evacuation protocol triggered. Passengers were walked off the train while the operations manager called in the teardown crew. The service disruption cost the railroad $3 million. The operations manager summed it up: 1 gallon of water. That is all it took to stop a 30,000-pound engine. The rest of the train sat silent. Every cold start hydro lock leaves a trail. Water follows gravity, maintenance follows paperwork. But the piston only knows force. When it meets a liquid wall, the outcome is never a stall. It is a fracture, a breach, and a bill that dwarfs the cost of a rain cap or a pipe fitting. Detroit, November 2018. A CSX intermodal unit sits overnight under a leaky shop roof. The maintenance log records a routine note: separator drain delayed, replacement part on order. No one flags the condensation pooling in the intake. By morning, water has collected behind the separator, hidden from sight. The maintenance tech clocks in and keys the starter. The engine cranks at 200 revolutions per minute. The starter motor amperage spikes to 610 amps. Cylinder number 6 encounters the incompressible wall. The piston halts in less than a crank degree. The connecting rod absorbs the full kinetic load. The steel yields. The rod bends, then shears in a single event. The crankcase wall fails at the bearing saddle. Oil sprays across the compartment, striking a signal relay. The result is a secondary collision, 3 crew injuries, $5 million in damage, and a written-off block. Ultrasonic inspection confirms a brittle, single overload fracture. No evidence of fatigue. The maintenance note is still taped to the separator housing. The tech's words are on record. If you skip a drain, you are betting the rod will hold. Water does not care about parts orders. It just waits. The teardown leaves no doubt. Hydrostatic lock is not a slow leak. It is instant mechanical death, triggered by a missed maintenance step. March in Calgary brought a spring thaw that flooded the yard overnight. Water pooled beneath the locomotive shelter, hidden until morning. The first shift found the number 2 cylinder of a GE AC4400CW locked tight. Starter motor amperage surged to 720. The piston struck water, bending the rod, fracturing it, and breaching the crankcase. Oil and coolant drained into the pit. The engine block was ruined. Recovery called for a remote-operated crane. The supervisor ordered power cut, the block rigged, and the remains extracted. 12 hours later, the engine was off the rails. Backup power kept the yard moving, but every lost hour meant thousands in costs. The supervisor's words remain: water doesn't care about shift change, it waits for steel. In Marysville, Washington, heavy rain collapsed a culvert beneath the main line. Drainage failed, flooding the approach. The yard engineer slowed the roll, but water entered the lead unit's air intake. Hydrostatic lock was immediate. The connecting rod snapped at the big end. The crankcase split. Diesel sprayed onto a transformer, sparking a small fire. Crews spent a week replacing the culvert, rebuilding the intake gallery, and reinforcing the embankment. The locomotive was sidelined. Only a fractured rod and a maintenance note remained. The note read, "Crankcase breach, cause, water ingress, drainage failure. Floodwater is indifferent. Civil infrastructure stands between water and steel. When it fails, recovery is measured in salvage hours, repair teams, and ruined engines." Clara City, Minnesota. October 2007. Rain pooled on the locomotive roof overnight, slipping through a split seam and running down the conduit. At 60 miles per hour, the prime mover surged in notch 8. Without warning, the crew felt a violent jolt. The number 3 cylinder struck water, not air. The connecting rod shattered, tearing through the crankcase. Shrapnel sliced the wiring harness. Oil and coolant filled the engine bay. Fire broke out within seconds. Emergency brakes engaged, but asymmetric braking on wet rails sent the train off the track. Tank cars ruptured, hydrochloric acid spilled into the ditch, and 350 people were evacuated. The logistics manager's log recorded, "Ingress at speed, no time to react, rod breach, crankcase rupture, hazmat release, Portland, Oregon, January 2026. 3 locomotives sat overnight in a flooded yard. Rain overwhelmed drainage, pooling at the intake vents. When the throttle opened, the middle unit sucked in water. The number 5 cylinder locked. The rod snapped, fragments punched into the engine room, and the electrical system shorted. Diesel sprayed and fire raced through cable trays. 30,000 gallons were released. Federal hazmat teams sealed the site. Crew members said it was like hitting a concrete wall at full throttle. Everything stopped, then everything burned. Spokane, November 2022. The prime mover was running at 720 revolutions per minute, deep in notch 8, when the turbocharger's oil coolant seal failed without warning. Pressurized fluid, oil mixed with coolant, shot straight through the intake manifold, atomized by the turbine's own exhaust force. The spray hit the number 7 cylinder like a liquid sledgehammer. In a diesel of this size, a turbo seal breach is not a drip. It is a high-velocity jet, driven by manifold pressure with enough momentum to fill a cylinder in seconds. The piston rose into an incompressible wall. The kinetic energy stored in the crankshaft, over 1,000 kilojoules at that speed, had nowhere to go but into the connecting rod. The rod reached its tensile yield in a fraction of a second. Metallurgical analysis found a clean transverse fracture with a narrow, heat-affected band, evidence of adiabatic shear, not fatigue. The rod snapped and the broken end punched through the crankcase. Oil and coolant erupted into the cab, igniting on contact with hot surfaces. 3 rods failed in sequence. The crankcase breach was wide enough to see daylight. A millwright on the teardown crew put it plain. "Water's got no give. You hit it at speed, it's like ramming a steel block." The rod never stood a chance. The aftermath left a textbook case, no gradual wear, no warning. Only a pressurized ingress, a solid wall, and a block torn wide open. Marysville's prime mover was running hot when the intercooler failed. Years of thermal cycling had worked a fatigue crack through the aluminum core. The original equipment manufacturer bulletin spelled it out. Intercooler tube sheet cracks can start below visual threshold. Failure is sudden and coolant breach is catastrophic. The crack was invisible at the last inspection. It opened under load, dumping coolant straight into the intake. At notch 8, the engine was pulling at 900 revolutions per minute. The charge air mixed with coolant. The number 4 cylinder drew in a liquid slug. The piston struck an incompressible wall. Pressure spiked beyond 1,000 megapascals. The connecting rod hit its tensile yield strength and failed in shear. The head gasket blew. The crankcase wall fractured. Oil sprayed across the engine room and struck the turbo housing. Ignition followed. Flames tracked the cable trays. The sequence was over in seconds. 3 rods failed in order, each one absorbing a fraction of the kinetic energy, each one snapping as the block split open. The original equipment manufacturer's fatigue bulletin warned that unchecked intercooler cracks propagate to catastrophic failure. Coolant. Ingress is silent. Fatigue grows in the dark. When it breaks, the engine does not stall. It self-destructs. The only warning is a spike in exhaust temperature and a surge in starter motor amperage. The aftermath is always the same: a breached crankcase, a burned-out compartment, and a maintenance log that reads hydrostatic lock, rod fracture, fire. East Palestine. The yard flooded overnight. Water pooled in the drainage pit beneath the lead locomotive. By dawn, the intake gallery had drawn in enough to fill multiple cylinders. The prime mover was already running at 750 revolutions per minute. The event recorder captured a sudden amperage spike of 820 amps, followed by an immediate collapse in engine speed. The starter motor did not stall. The engine seized. The ingress pathway ran straight from the drainage pit into the intake manifold. Water bypassed the air filter, entered the combustion chamber, and waited. As the pistons rose, they met a wall that would not move. The number 4, number 7, and number 11 cylinders hydro-locked in the same revolution. The rotating assembly did not slow. The force traveled through 3 connecting rods at once. Each rod met the incompressible wall and exceeded tensile yield in milliseconds. The rods fractured mid-shank. The fracture surfaces showed no sign of fatigue, only brittle overload. The crankcase wall behind cylinder number 4 split open along a chevron-shaped line. Oil and coolant erupted, spraying 2,000 liters across the engine bay and onto the adjacent fuel tank. The breach was wide enough to expose the main bearing cap. The engine block, 30,000 pounds of cast steel, failed at the seam. The NTSB investigator called it a textbook multi-cylinder lock, not an engine drowning. Catastrophic mechanical rupture. The crankshaft kept turning, but the rods hit a wall. Within 2 seconds, the prime mover went from full power to total structural failure. The chain reaction was over before the crew could reach the cutoff. 3 rods failed in sequence. The chevron breach marked the direction of force, always away from the locked piston, always toward the path of least resistance. The teardown would show embedded rod fragments and a crankcase aperture that left daylight visible through the block. Teardown begins in silence. The block sits on steel stands, its crankcase split wide open. Oil and coolant streak the bearing caps. The millwright's gloves are black with residue. Each fractured rod is tagged and measured. The break in the number 4 rod is clean, transverse, and bright, a brittle overload. No sign of fatigue. The chevron breach in the crankcase points toward the locked piston. Embedded fragments are recovered from the aperture. The main bearing cap behind number 7 is deformed. The crankshaft journal shows a single impact mark, not a wear groove. This is not progressive damage. It is a single, catastrophic event. The event recorder is pulled. ELR data shows an amperage surge to 820 amps. The spike lasts less than 2 seconds. RPM collapses from 750 to 0 in a single sweep. The alarm specification for this series is 650 amps. Anything above that is out of tolerance. The system should have tripped an automatic shutdown. It did not. The NTSB report notes the absence of a functional amperage alarm. The failure allowed the prime mover to attempt a full compression cycle against a solid wall of water. Mandates follow. All 16-cylinder units must now carry real-time amperage monitors. Any reading above 650 amps triggers an immediate engine room shutdown. Quarterly ultrasonic inspections of intercoolers and coolant lines are required. Cracks below visual threshold are grounds for service withdrawal. The FRA issues a bulletin. Hydrostatic lock is not a gradual failure. It is instant mechanical rupture. All event loggers must preserve amperage and RPM traces for post-incident review. The millwright's final note is brief. Rod failure at the shank. No fatigue. Overload only. Water in the cylinder is a wall. The engine cannot negotiate with physics. The teardown is complete. The lessons are written in steel. Every modern prime mover is one cracked gasket away from a hydrostatic lock. At 900 revolutions per minute in notch 8, a gallon of water becomes an incompressible wall. The connecting rod doesn't bend, it shears. The crankcase doesn't contain, it ruptures. This isn't drowning, it's mechanical execution dictated by the laws of physics. In heavy rail, The smallest leak means the next catastrophic breach is already counting down.